welcome to this tutorial on creating good 3D figures with minimal effort. So, we're not going to lie. I think it's a day where it's a bit difficult to be cheerful, but I'm going to try to start with a cheeky joke, okay, which is who do you want to trust? Although we just had lunch together, okay? The same sandwich, roughly, the same ingredients, at least, like wheat flour, jambon, maybe some butter, but on the left, you have it packaged, as a triangle sandwich on an aire d'autoroute with soundless packaging. And there you have this delicious fresh sandwich. Okay, are you salivating yet? And basically, I think you already see where I'm going, what I'm hinting at. Whenever you read a paper on 3D geometry, are you going to trust the paper that displays maybe a trefoil knot using default matplotlib settings, or do you prefer these figures? Okay, I'm sure you guys prefer this one. Just in terms of aesthetics, but also in terms of message. I think you understand more what is going on with this figure. And basically, the big message of today's talk is that to go from here to there, I just used 10 lines of PyVista code. Okay, 10 lines of Python code, yeah.
People prefer Trump,
Yes. No, it's true. But
okay, the left side, we see the triangles, and in a sense, we see the ground.
Exactly. Okay, so it's actually going to be something that I discuss in like 10 slides, which is that maybe as mathematicians, we have this fetish for low resolution triangles, but actually there is actually very little good reason to prefer this over the smooth interpolation, which is just as efficient to compute. Okay, so obviously the promise of today's talk is to go from here to there, and I'm going to show you how to do it efficiently. But maybe, I know that I'm talking to a mathematician's crowd, maybe you're not convinced. Okay, maybe you think that it's wasting your time, creating great 3D figures, it takes some time, definitely, but I'd like to highlight a few salient points. First, that you're lucky, especially if you start your PhD now, in the sense that those kind of figures can now be rendered, implemented in minutes using PyVista, which is a transparent matplotlib replacement. So, me during my PhD, I had to do weird hacks with like Paraview. Maybe people like you, Surya, have to learn how to use Blender. It's very time consuming and it does not mesh well with the rest of your work in data science, medical things, etc. But no, today it's incredibly accessible. The second thing is that using great figures allows you to demonstrate visually a familiarity with the state of the art in geometry processing. And I think that's important. You need to show that you know all the tool chain, all the tools well. And so whenever you display those kind of figures, basically you are signaling that you know the state of the art in terms of graphics. So people are more likely to believe that you also know the state of the art in terms of, shape analysis, statistics, etc. So that's visually very important. And also it sets you apart from the low efforts paper that are flooding your reviewers' mailboxes. It's something that we rarely discuss, but I think it's important for you to know about maybe the statistics in terms of acceptation rate, etc. Me, every year, for instance, I review for NeurIPS. Okay, and at NeurIPS, basically the game is that I get 6 papers, and I need to flag one for publication. That's roughly, 1 or 2. And the thing that I have to say to you is that out of those 6 papers, it's actually very easy to at least do a first sort, because at least for me over the last 4 or 5 years, all the time, out of 6 papers, I get 2 or 3 papers which are very clearly written by like master students who are, submitting their master's projects and hoping that it's going to get published, because especially in the US, you need to have published papers to get accepted in graduate school. So that's a thing. So basically those ones, you immediately see that it's written by someone who does not know anything about the literature, etc. So it's an easy reject. And then the next 3, typically, it's sometimes the question is not very interesting, sometimes it's a bit misguided, etc. But my experience is that the statistics roughly hold true. And basically, by using those kind of figures instead of those ones, you immediately signal that you are not one of the low effort junk papers that are clear rejects. Okay, so that's important. So maybe the world champion at this game is Keenan Crane, who's a very well-known graphics researcher, professor at Carnegie Mellon University, because basically he really perfected this game and he signals competence with every single figure on his website. So it's actually very interesting just to read, me as a researcher, I like reading his papers just because they are so well illustrated. I know that I'm going to learn something interesting every time. So I think this is a kind of aura that you want to project to your colleagues. Now, among all the different tools that I could use to do this tutorial, I will focus on the visualization toolkit, VTK, instead of Blender, for instance, or Houdini, etc. And the main reason for this is first that VTK is extremely reliable, I think. It's been going strong since 1993. It's developed by Kitware, which is a company which is mostly funded actually by public research projects in the US. It's actually the company that was founded by the guy who invented the marching cubes algorithm, for the story, and unfortunately who passed away a few years ago. And basically, I think it's a good tool of choice in a scientific setting because it is designed for scientific visualization. So you have all the nice functions, API, etc., to display scalar values, to display vector fields, to change color maps, all of those kind of things, which are a bit more tricky to do with video game or graphics-oriented software like Blender. So that's the kind of core engine, VTK, a big C++ monster. But fortunately, you won't have to access it through the VTK C++ API. Nowadays, you can use it through basically two main open doors. First, it's PyVista, which is a Pythonic wrapper on top of PyVTK, which is a barebone binder on top of VTK, which is basically Matplotlib, but 3D. Okay, so that's exactly what you expect. And then I'm also going to talk about Paraview, which is an interactive graphical user interface. And I want to be clear on the fact that everything I show here with one of those tools can be done with the other. Because at the end of the day, it's the exact same engine. You just need to know where to push this button or where to activate this lever to get this and this.
Who develops PyVista?
What?
Who develops PyVista?
PyVista, it's developed mostly by geologists in the US. So the thing is that the core, it's really VTK, like the magic comes from VTK. And you have basically PyVTK, which is the stuff that is actually maintained by Kitware. You write in Python code that is very C++y. Like you really feel that you are writing C++. And the thing of PyVista, if you look at the code, I mean, it's very easy. It's just that it wraps 5 or 10 lines of PyVTK code into one clear Pythonic function code. So that's the only thing. So, in the very first Shape seminar, WePusual presented Vido, which is another alternative on top of that, but it's much less well maintained, documented, etc. So I would advise using PyVista for the moment and maybe look at Vido for tips on what can be done with this engine, especially in terms of interactivity. So that's the thing. So today's talk is very much about demystifying the graphics toolbox, because even though you know that PyVista is a good library to use, you probably do not know what are the proper functions to call to get this or that effect. So for instance, if I talk about subdivision, culling, SSAO, or PBR, probably you don't know what I'm talking about. But each of those 4 terms is actually super useful. Okay? So me personally, I remember my very first interaction, for instance, with Benjamin Charlier, was in Cachan, and he showed me how to do great figures, with tricks, with Paraview. And basically, I'm trying to do the same thing here today. Okay, just to show you basically the interesting bits that I stumbled upon by reading this VTK documentation over the years. Okay, then I'm going to show you quickly links to advanced resources, because all of that is not dark magic. It's actually very interesting mathematics, the material models, etc. So basically links to the math behind the simple functions. And then finally, if we have time, I'm going to show you quickly an interactive Paraview demo, just to demystify a bit all of those buttons. with some real data, a real CT scan. So first, okay, you have already done ppin style PyVista, and then you just want to import the library as PV. And then how do you get this figure? Okay, well, it's basically matplotlib code. Okay, so first you create a window, so which is known as a plotter. So that's why most PyVista code, it's like PL dot something. Okay, but that's because PL, it's your PV plotter, your PyVista plotter. Here I decide to create a window with 800 by 800 pixel buffer. And then I create data, and probably most of the time you're going to deal with polygonal data. What is polygonal data? It's given by basically an array of points, which is an n by 3 array, so x, y, z, x, y, z, x, y, z, and then an array of faces. Okay, and here it's maybe a bit surprising because what you would expect probably is to give triangles or to give edges. Okay, but polydata is more general than that. It allows you to handle pentagonal faces, those kind of things. So actually, what you give to PyVista, to the VTK engine, is more like a list of faces, and it always starts by the number of points that belong to the face, followed by the indices of the faces in the point arrays. So basically, if I want to define a triangular mesh, my faces array is a list of numbers that goes like 3 ABC, 3 DEF. And so this just means that if A, B, C are equal to 0, 1, and 2, it just means that my first triangle is a triangle that is defined by this point, this point, this point, etc. So in practice, if you have triangles, an array of triangles as an n by 3 array, you just add columns of 3, you reshape the stuff, and you get what you want to work with. Okay? Then you just have to add the mesh into the scene. And then you do what you would expect, which is you set up your camera location. Here, with this specific data, I want to look at it from above. Maybe you zoom, and then we're going to see, maybe you enable entire aliasing, parallel projections. Anyway, then you show your figure, and you save it as a JPEG image, and it just works. Okay, you get this. That's a flat 3D rendering of our trefoil knot. Now, first, what is this anti-aliasing thing about? Okay, by default, it's activated, actually. So it's just that if you had not activated anti-aliasing, and if we were working with low-resolution windows, like a 200 by 200 window, if I disable the anti-aliasing, I just get one sample per pixel, and it looks rough. So instead, you enable anti-aliasing, use multiple samples per pixels, and you get something smooth. Just that. Then the other lines that I used was enable parallel projection. And this is mostly a matter of taste. It's just that by default, you get this 3D perspective, where objects that are far away are smaller than objects that are closer, etc. But maybe I never like that. I always prefer this like Age of Empires 2 rendering. And so I prefer to enable parallel projection. Also, and I think in a scientific context, it makes sense because you want to be able to measure things, etc. It just flatter. It corresponds to having a camera at infinity. Okay, so the light rays come parallel to the window, like isometric rendering. Now, that was the very first step. And so now we're going to talk about smoothness, because as Alain Trouvé said, oh, maybe we prefer triangles. I would argue that maybe not. Okay? So first of all, a simple trick to know is how do you go from this kind of picture to this one? Okay? Basically here, in practice, you just add a new parameter, which is add mesh, with the smooth shading property set to true. And suddenly you get this, okay? You get this picture. So what you can remark is that this picture has the exact same geometry as this one, okay? Like if you look in terms of 3D boundaries, it's the same one. What has changed is that when the computer wants to determine the color of a pixel, it has to perform what we call a shading calculation, where you compare the angle of the incident light with the angle of the normal, and then maybe you do dot product, something like that. And by default, when you use flat shading, the normal of the triangle is supposed to be constant on the face. But if you use smooth shading, basically the normal is going to be linearly interpolated along the face. Okay, so actually, PyVista is computing point normal at vertex locations, and then you interpolate, and so you immediately get the smoother value. So that's already a first step.
Can you explain what's happening when you call add mesh? Like it's creating the graph with the edges?
Yes. So basically, the object is already created here. And with add mesh, I am adding a new actor to the plotter object, which is the one that handles the object and the camera. And it's just that when I do show, the plotter is going to make a loop over all the different objects in the scene and rendering them to the screen. So I don't know if that's clear. So add mesh is just like making a pyplot.plot command or something like that. So that's the first step, but then you can, it still look rough. So what you can think about doing is to add more triangles, right? So here and adding more triangles is known as subdividing in computer graphics. So basically you can say before adding S to the scene, I'm going to say S equals to S.subdivide with a method. So by default, you use the linear method and a number of subdivision because this is going to be a recursive algorithm. So here, subdividing with 0 steps is just the identity. So I keep the same mesh, but for clarity's purpose, I'm displaying it on the left using flat shading and highlighting the edges, and here, as a smooth shaded object. So if I use one step of subdivision, basically what you see is that each triangle got subdivided into 4 triangles. So in terms of topology, it's very simple. And in terms of geometry, it's also very simple here because the vertex locations of the higher resolution shape are just computed using a linear interpolation. So I can do it again. Okay, if I do that, basically I do not really change the geometry. Okay? So I'm just changing a bit the smooth shading here because now the linear interpolation thing just happens closer to the edges, but basically it doesn't look great. That's not what we want to do. Instead, what you can use is a more clever subdivision surface method, which is, for instance, the loop algorithm. You have other methods. It's typical early computer graphics things. Okay, and with a loop subdivision filter, this is what you get. So at step 0, identity. At step 1, you get this. Okay? So actually, in terms of topology, it's equivalent to what we are doing before. We are just subdividing triangles into 4 smaller triangles. But now, basically, clever computer scientists came up with an interesting formula to have smoother interpolations of vertex coordinates along the mesh topology. Okay, so this is what you get. And it immediately looks better. I think we can agree. 2 subdivisions, 3, 4. Okay? So if I come back, this is your raw data. Bam, bam, bam. And to be clear, so this is something that comes at very little cost for you. And actually, in video game hardware, this is actually supported, at the hardware level, actually those operations. So you have to realize that, memory bottlenecks, memory transfers are the main bottleneck in video game graphics. And so when you see a scene that is rendered with millions of triangles, actually, it's very likely that the video game engine just sent a relatively low resolution mesh and subsampled it on the fly using those kind of methods. So maybe you see that and you think that, Jean, you are cheating. This is cheating. But I would argue, no, we are mathematicians. I mean, we're not afraid of using C2 interpolation, smooth spline interpolation. It's fine. There is actually no good reason to stick to linear interpolation for data that is going to be smooth. So, because basically here, it depends on the method, but typically the positions of those vertices actually stay there. It's just that you change the way you interpolate between your samples. So in terms of signal processing, it's actually completely fine. It's just that we project onto a set of C2 functions instead of projecting onto the set of piecewise affine function. Okay. So by the way, okay, it's a bit of a gimmick, but an advice that I could give you, if you present your PhD, etc., is maybe you can actually 3D print the shapes that you are dealing with. It makes it, for example, for me, the first time this happened, I remember it very well. It was in Oberwolfach. It was a researcher who was working on like architecture with polygonal faces, etc. I think you still remember that.
X-meshing, yes.
Exactly, And so I still remember this talk just because I was given a 3D model. So, I did it for you. So maybe, in terms of hygiene, it's not the best. So, I don't pass it, but the rank, you can look at it afterwards. So this is a low resolution mesh, and this is a high resolution one, and it's smoother. It feels smooth. Okay. So if you can do it, why not? I'd be happy to discuss it with you afterwards. So, just to tell you that, for instance, last week I was at the Smiley Sigma conference, which is very much about those kind of mathematics. Actually, there's a lot of interesting mathematics behind subdivision surfaces. It's heavily tied to the theory of splines. So if you look at Bernstein's polynomials, the Castelview algorithm, it's actually a one-dimensional version of this. So you implement a recursive algorithm that actually gives you polynomials of increasing smoothness orders. Or maybe you've already heard about the Nash theorem about the embedding of Riemannian manifolds into R3. And there's a very famous illustration, at least for people of my generation, which is of a flat torus that is embedded in R3 by the HeKA project. And so this is a donut torus, okay? The one that you know. So it has a topology of a torus, but it does not have the same geometry as R2 quotiented by Z2, okay? Because unfortunately, here with this torus, this length, the inner length, is smaller than the outer length. Okay, and that's a bit underwhelming because some, mathematicians typically tend to prefer the flat torus, which is the world in Pac-Man, for instance. Okay, just a square, and when you go up, you come back down. And basically, the theorem that tells you that there should be a way of getting an immersion of this flat torus in R3, which is both smooth and isometric. And the people in Grenoble, among whom Boris Tiver, who was with us 2 weeks ago, it's possible to render the image. And the way you do that is you do a bit like a subdivision surface, but you add corrugation that are going to change the local geometry. So this is step 1, step 2, step 3, step 4. And actually what they showed, if I'm not wrong, basically they showed that if you had the real object in your hands and you took a picture, this is exactly what you would get. It's pixel perfect. And the idea with this surface is that with all those corrugations, basically you are changing local length so that basically the inner circle, if you look at it at a core scale, it seems to be shorter, but you have so many oscillations that actually its length is equal to the length of the outer circle. So it's pretty nice. That's the kind of things that are behind this loop subdivision algorithm. Okay, just to convince you that it's not cheating. It's fine. Okay, so but that's all fine. It's all white objects. Maybe you want to add colors, to display signals. So how do you do that? The thing that I'm sure you will have found yourselves is that when you add mesh with PyVista, you can specify a color map. It's exactly the same API as Matplotlib, and actually PyVista supports all the color maps that are already supported by Matplotlib. Okay, so here I'm adding a mesh S. I'm displaying as a signal just the Gaussian curvature that I can compute very simply here for this smooth mesh using PyVista. So I specify an array of scalar values. I clamp the values to -1, 1, just to have nicer results. And then I just choose my color map. So here it's Viridis, here it's Plasma, what you'd expect if you're familiar with 2D Matplotlib. Then maybe you say, oh, I want to get white for flat, for zero curvature. So I want to get a symmetric color map. So you look around and you end up on different color maps that seem to be the same, right? So here, Cool Warm and BWR for blue, white, red are two color maps for which 0 corresponds to white, positive values corresponds to red, so that's what you see here, and negative values correspond to blue, right? But you see that they do not feel the same, right? Because here, for the same data with BWR, you get the feeling that there is a kind of there seems to be a kink here, at least for me, whereas here the transition is smoother. Okay, so here I'm not going to delve too much into the topics here, but there's a very interesting literature on color maps and perceptual colors. So if you've never seen that, you have to know that the RGB color space is actually not at all perceptually accurate. Actually, Jonathan, maybe some of your research is about that. It's just that the RGB color space is just there for historical and technical reasons. But for instance, linear interpolation in RGB color space does not match at all our intuition about what is linear steps in color space. So something which is a bit closer is, for instance, this Mundell perceptual color space, where you have all the perceptual colors in a 3D space, and it's like equispaced, so that I think you would agree with me and with Professor Mundell that it feels isotropic. Like it feels that all steps here, all colors between cubes are the same distance at each other, in all directions. But then you see that you end up with a color space which is not at all a cube. It looks a bit weird, etc. So be aware of that. And actually, the Matplotlib library has a pretty nice tutorial on the topic, okay, where you see for all of the standard color maps how do they feel in terms of lightness, etc. When you print them, if you have if you see 2 colors instead of 3, etc. It's just an advice. Be aware of the fact that color maps can highlight and hide different things. Now, so another thing is that maybe you would prefer to have a blue for positive values and red for the others. Okay, just a simple trick is that whenever you see a color map, if you append underscore R at the end of the name, you get the reverse. Just a simple trick. So this is RDBU, red to blue, and this is RDBU underscore R, which could have been named blue to red. Okay, but it's not there. So now it's fine, but you would agree that it doesn't look that great. It looks a bit too shaded, right? Too dark. So how do you change that? Well, you have commands to explicitly set up your lighting system. So the first thing, which is very easy, is to cheat by adding ambient glow. Okay, so when you add your mesh, by default, the ambient value is set to 0, which means that the object is not an LED object that exudes light, but you can change that by just saying, for instance, ambient equals 0.2. Okay, and then you get this kind of effect. Why not? Instead, what you can prefer is to, if you like to film movies, etc., is that you have all the interface you need to set up as many lights as you want with different properties, different colors, etc. Okay, so it's known as a light kit. So how do you do that? First, when you create your plotter, you're going to disable the default light kit, which comes from a VTK that contains, I think, 5 lights. Okay, you say no, I want perfect control, so you remove it. Then you add your mesh, and before making the show calling pl.show, you just add lights. So here I'm adding a first light with an intensity of 0.7, which is going to be directional. So imagine that you have a light source which is at infinity that sends us parallel light rays. So I just specify using two angles, like azimuth and equinox. I forgot, but you specify from which direction the light comes from, and then you add the light. Then I add a second light, which is going to be a headlight. And so headlight, it means that basically it comes from the camera. And here, I have the same intensity for both lights. Okay, so 0.7, 0.7, I get this effect. And obviously, if I change the ratio, I change my scene. So here, I have upped the directional light and dampened the headlight, so I get this. And if I want to get a mugshot, I do that. So a flash, I increase the headlight and I dampen the directional light. So you can play around with that. Now, that's all well and good, but you see that by default there is no shadows. Okay? PyVista does not compute occlusion and shadows, but it's actually very easy to enable. Okay, to do that, before calling your show pl.show function, you just have to call pl.enable shadows. Okay, so this is the default rendering, and this is with shadows. Okay, and the whole point of using shadows, hopefully, is to make your figures more realistic and or easier to read. Okay, and I would argue that here in this scene, for instance, it's more realistic, but it's not really easier to read, right, with shadows. So depends. So you have two other options, which I think are worth knowing about, which are about computing fake shadows that are more uniform, but which are here only to make the scene easier to read. So the first one is something that I really like. It's called Screen Space Ambient Occlusion, SSAO. Okay, so this is a rendering that you get with SSAO. And to be clear, okay, what SSAO is about is that when the algorithm renders the scene, it has access to what we call the depth buffer. So it knows that, for instance, this point is at the forefront and this point is more behind. Okay, and when I enable screen space ambient occlusion with a given radius, what I'm really doing is that I'm asking PyVista to compare the depth of each point with its surrounding at a given scale. And basically, if the point is behind its neighbors, it's going to be shaded. And if the point is at the front of its neighbors, it's going to be more, basically more in the light. Okay, so you see that with screen space ambient occlusion, the object kind of casts shadows behind. There's another mode, which is known as eye-dome lighting, where instead, it's more that the silhouette is highlighted. So, here the shadows is cast there on the outside. Here, it's as if the shadow was cast on the inside of the tube. So I don't really use that, but it's interesting to know that it's there. And actually, it's actually part of a PhD of a French engineer who did his PhD with EDF, for scientific visualization, non-realistic photo rendering. So, and maybe a bit of a joke, but last week I was with Joshua in Marseille, and we really, I told him, you know what? I really prefer screen space ambient occlusion over that, because in Marseille you had a lot of lighting, nice shadows, etc. And me, whenever I see that, I think, oh, it looks like a video game. Maybe because I grew up in Paris, where you have this very ambient, diffuse lighting all the time. So for me, in a sense, this SSAO looks more realistic than this. So this is personal taste. I don't say you have to think the same, but at least now you know the options. So then you can...
Yeah. There are simple ways to add shadows on the back front of the diaphragm.
Yeah, so actually, it's something that Robin discussed with me 2 days ago. I hadn't realized that it would be interesting to show. Actually, I don't know how to do it simply. other than just adding an explicit plane behind, to catch the shadows. But no, I don't really know. No. Sorry. Maybe there's a way to do it. Maybe there isn't. I don't know. Because it's true that it's a common technique to increase the readability of a figure would be to add, a cast shadow of the object under it. So I would start doing it with a plane, but I don't. Okay. So now you say, okay, it's fine, but it still looks very early 2000s. Okay. And why is that so? That's because the way our object catches the light is not very realistic. And it's actually typical from computer software of 25 years ago. But, we are not in 1995 anymore. We can afford more complex formulas. And basically in VTK, the more complex material models are hidden behind the PBR letters. PBR for physics-based rendering. So the idea here is that actually, if you look at a material, you have the outer geometry that can be specified using triangles, blah, blah, blah. But there's also a microscopic geometry, like you have tons of facets, etc., which is going to determine how your object scatters the light. Okay, you have to imagine that this is what happens. So in practice, if you take a sheet of material and you have light that comes from a given direction, most of it is likely going to be reflected, using simple reflection laws, but part of it is also going to be diffused in all directions. So, this is actually what changes the feel of different materials. And in a computer program, all of this is really encoded by a function that should tell you for any triangle with a given normal orientation, assuming that light comes from this direction, so you have this angle theta, and that you are looking at it from this direction, so basically you have two angular parameters, how much light has been transmitted, from the light to the camera. And this is what is known as a material model. And basically, this unrealistic feeling comes from very cheap formulas, where you take a dot product, you square it, and you're done with it. So that's really the idea. But nowadays, you have more expensive formulas have been implemented, and we are very lucky that they have been added into VTK, basically between 2019 and 2022. And this has been done especially by Kitware Europe, by engineers that are in Lyon. So if you look, at the blog post that introduced those features, that's very French names, okay, that added this, mostly because, VTK takes money from the US government, to improve visualization of large HPC simulation, but they also take money from like EDF, those kind of companies. And for those companies, they're happy to be able to visualize streamlines, etc. But if you want to show off to the executive, you also need some photorealism. So that's why they blended those two features together. Now, so basically, it's super simple to use in PyVista. The only thing you have to do is when you add your mesh to the scene, just like you added colors, you set PBR to true, and then you specify mostly two independent parameters. The first one is metallic. The second one is roughness. Okay, I'm going to show you what this looks like. So when metallic equals to 0, it means that your object is more like a plastic. When metallic equals to 1, it means that it behaves like a metal. And metallic equals to 0.5, it's like a superposition of the two. And then roughness, okay, when it's equal to 1, it means that your object diffuses light in all direction. Like for metal, it looks like brushed metal. But when roughness is going to decrease, we're going to see specular reflection light effects. So on the left, you have metallic equals to 0. On the right, you have metallic equal to 1. And then I'm going to lower the roughness parameter from 0.8 to 0.4 to 0.2. Okay, so I think on the left, it's pretty convincing. Okay, so, it's kind of, I go from a very rough to a very smooth plastic object. So it looks like that. I think we are pretty happy. I think you would agree with me that what happens on the right is very underwhelming. Okay, because we went from depolished metal to something very dark. And then you say, what's happening? Actually, me for a long time, I thought that it just meant that the PBR engine of VTK was a bit shit, was a bit underwhelming, and that was it. But then I just paid more attention to the tutorials, and I realized that I had forgotten an option. You know, it's very easy to forget those options, which is that, you know, metalness is all about reflections. And it's just that when you have a smooth metallic object, it means that its color is very much determined by the environment. Okay? And it's just that by default, in my scene, I have no environment. So everything happens as if my object was alone in a dark room. So that's why it's getting very dark. So what I have to do is I have to specify what the environment looks like. And you do that with a cube map. Okay? So it's explicit in the tutorials. I say cube map. I download basically this kind of image, which is basically a collection of 6 JPEG images that tell me that, okay, it's a cube. So in 4 directions, I have landscape. At the bottom, I have the soil, I mean the ground, and on top I have the sun. Okay, so I specify that. And then I just add it as an explicit environment texture. Okay, and this is going to fix my metalness problem. And then maybe not, maybe you want to display the environment in your screenshot. So to do that, you have to add it explicitly as an actor. Okay, in the next pictures, I disabled it because I like the white background. But then, okay, you just use your lights. And also the thing with PBR, physics-based rendering, is that it's conservative in terms of light. So actually with default light parameters, it's a bit dark. So I prefer, you know, to increase it. And maybe one of the things that I regret in PyVista is that currently you cannot add a light with an intensity beyond 1. So instead what I do is that I add several lights with an intensity of 1. Okay, so I hope that in a few months it's going to be fixed, but currently that's what we have to do. And then it looks like that. Okay, so I come back to my roughness equals to 0.8 figure, metallic, and here just for a change, half metallic, half plastic. And then I'm going to lower the roughness. Ta-da! And it looks great. Okay, so, and it's not that slow to render. Like, you know, everything I've shown, it's just a notebook. You can download it on my webpage. It's a few seconds, right? So you do not have to wait forever to get those pictures. And what you can see here is that basically you see the reflections of the environment. So you do what you want. You take whatever environment you prefer for a picture. So that's one thing. So you see that, you know, it can get pretty realistic. You can do, you know, the one ring thing. Okay, but here maybe you have too much lighting, so it doesn't look that great. And maybe you're more into anime, you know, just maybe. So instead of going into the physics-based rendering path, here I want to show you how to get a more like artistic, or at least anime-like feeling with silhouettes and animations. Okay, how do you get good-looking silhouettes with those 3D renderings? So what do I mean by that? Basically, what I want to do is I want to highlight the contours of my 3D shape with a black line. You know? And the simplest way of doing so is to use the explicit silhouette argument in the add mesh method. Okay, so I said that silhouette should be highlighted with a line width of 10 and a black color. And what it's going to do under the hood is that when the algorithm renders the image, it's going to extract the edges of my mesh that look pretty tangent and highlight them with a bold marker. So that's what we see here. And actually, I don't know if you can see it on the screen, but if you zoom in, it's a bit granulated. Okay? Because ultimately the effect depends on the smoothness of my underlying triangle mesh. So it's very fast, very easy, but not so great. And probably, at XP, you want to be a bit of a perfectionist. So there is another trick to get better looking silhouettes. And the way to do it is to use those few lines of code. Okay, basically the trick is to say, okay, how do I get silhouettes? Maybe what I could do is I could take my mesh, I could inflate it a little bit and paint it black. And then I could show the two objects together. So if I just show you my original object and its highlighted counterpart, you just see the highlighted counterpart. But what I'm going to do is that when I'm going to display the black inflated object, I am not going to display all the triangles that are facing the camera. And so basically this inflated mesh is going to look like a shell that sits behind the object, just so that it highlights well the silhouette of my object. Okay, and this step is known as culling. Like you cull the herd, you remove all the triangles that you do not want to see. So what does the code look like? So here, basically to inflate, I want to use a warp by scalar Paraview, like VTK filter. And
works well if your mesh is well oriented.
Yes. No, exactly. So for triangle shapes, maybe you want to do so. But when you compute your point normals, you have filters that are going to try to get consistent orientation, etc. So when I warp by scalar, by default, it's going to change point coordinates by a factor along the normals. And me to specify a constant factor by default, I just create a scalar field which is equal to W times 1 for all points. So I create a vector of W's, and then I warp by scalars using the name of my vector of W's. So this is to create my shell. And then I just display my shape. I also display the shell with black color. I curl the front thing, and then I get this. And then, for instance, I can increase the width of my shell, and you get this type of rendering. So here it's a bit too much, but personally, I really like this one, for instance. Okay, so just to tell you that you can do that, and you can also do the same in Paraview. Everything I show you have explicit buttons in Paraview to do it. Okay. So now, maybe final steps is that you want to create movies, animations, and that's very easy. So the first basic things, if you are doing crazy things with your data, maybe you can just write a for loop. You take screenshots, and at the end you collate them with FFmpeg. Okay, if you do crazy things. Otherwise, you can just use the PyVista API, which basically does this for you. So instead of opening a picture, you open a movie. So an MP4 movie, for instance, with a quality of 10 because you want high resolution quality compression. Then you write your loop for every frame. You update in place the point coordinate, the signals. You write your frame, you close it, and you get a video file. So here, that's what it's going to look like. Just basic curvature flow written using a simple Paraview loop, a simple VTK loop. Okay. Just to say that it works. Well, like it's so much easier than when I was a PhD student. That's completely insane. Okay. And final steps, maybe, you want to also show textures. So the first thing that you can do is to define custom RGB, maybe RGB alpha vertex colors. Why not? So that's very easy. When you add your mesh, instead of specifying a color map, you set the RGB parameter to true. And then if your scalars array was an n by 3 or an n by 4 array, it's going to use it to display colors. So here what I do is I use as colors my point coordinates. Okay, and the thing is that the convention here is that RGB values are clamped to 0, 1 modulo. So basically here, my shape actually sits in like the -3, -3, -3, -3, -3 cube. So you're seeing this thing because basically you're going from like 1.1 to 2.0 along the edges of the cube. So that's why it looks like this. Maybe instead, for instance, here I'm displaying the point normals. So at each point I have a vector which sits on the unit sphere. So if I take this vector, I add 1 and I divide by 2, I get an RGB vector which sits well, in the unit cube. So that's why it looks smooth. Okay, so that's just point normals. And for change, I used shadows instead of ambient occlusion. So that's if you have explicit point coordinates, as we often do, point colors, as we often do. But instead, especially if you work with artists, you prefer to use textures, which is that basically colors are encoded in a JPEG image, and you want to find a way of putting your point vertices in correspondence with points on the JPEG image. And the way to do that is to specify texture coordinates, which by convention are known as U and V. So here I'm displaying the UV coordinates of my points, on my trefoil knot. So that's what they look like. So they're just numbers between 0 and 1. And then to use them in my rendering, I have to say that s.active texture coordinates are equal to this array of size n points by 2. Then I can write my own texture image. Okay, and this is what I did. And then when you add your mesh, instead of specifying scalar values, you specify your texture. So say texture equals to pv.readTexture this file, and you get this. Okay, you do whatever you want. So going further, PyVista supports like GLTF models where you use texture for material properties, like you specify local roughness, metalness, everything. Like it works. So for instance, if you want to play around, you can download assets from something like Polyhaven. Everything is free on this website, and you use them with PyVista. There's a tutorial. You import GLTF, it works. Okay. So that's if you want to show off at SIGGRAPH, but medical imaging probably it's a bit useless. Going further, maybe what's more interesting for us is to know how to display arrows, to do like DMM, those kind of things. So you can do that. There's a tutorial for it. That's why I recommend PyVista. The keyword is glyph. Maybe you also want to display a point cloud, but where every point has a different color, a different radius, those kind of things. Okay, the thing that it took me several years to realize that actually this is what is hidden behind the point Gaussian name. Basically, if you want every to have a different shading, a different aspect for every point, you need to use a point Gaussian tutorial with different settings. And you say, no, instead of having a Gaussian, use a small sphere with a edge color, those kind of things. You have a lot of legacy strange things in the API. This is one of them. Going further, everything I told you is very well documented mathematics. That's very interesting. So if you want to learn more about that, I would advise you maybe to have a look at this Branch Education YouTube channel that provides deep dives into modern hardware. Basically you see the link between what I showed you and the actual physical circuit. And if you want to know more about the algorithms, I highly recommend the lecture notes, the lectures of Jem Yüksel, who is professor in Utah, in the University of Utah, who teaches class about computer graphics and interactive computer graphics, and it's fantastic. And for instance, for ambient occlusion, there's a whole 1 hour long video on what is ambient occlusion, how do you compute it, and that's very, very interesting. Like all the different tricks. I mean, for me, it taught me basically what our hardware is capable of, beyond what we already know with PyTorch, etc. Okay, so that's it for my presentation. It's already 54 minutes, so maybe I should stop here. I don't know what you think. Oh no, maybe I show you briefly how Paraview works. Okay. So you seem to be happy to see that. Okay, so let's take 15 minutes just for me to open Paraview and demystify a bit all the buttons. Okay. So first, to be clear, what is Paraview? Oh, there is no internet. Okay, no problem. Okay, I'm not going to try to connect to the internet. You just go on Paraview and you download something and you get the software, right? So for instance, even with Linux, don't bother with apt-get and stuff like that. It's too complicated. Basically what I do is I download this big 600 megabytes stuff, you unzip it and you get Paraview version 5.13. Okay, just do that. You get a file and then you go in the folder, you go in the bin subfolder and you want to launch Paraview. On Windows, I assume it's paraview.exe, something like that. And then bam, you get this window. So very intimidating at first. What are the important things? So first, let's have a look here. A file, which is to load file. I never use it. I just drag and drop data. Then you have edit. Never use it either. Or maybe file is useful if you want to do movies at the end. You save screenshots, etc. Then you have view. Okay, view is important because with view, you can hide or show different panels. And by default, you have the information and properties and pipeline browser panels that are open. I also always open the color map editor and the light inspector. Light inspector is to set the lighting. Okay, so you just do that. Then you have sources, a bit useless. It's if you want to add explicit spheres. Okay, filters, it's where the magic happens. Basically, filters is you have many VTK functions are there. It already fills my screen if I do alphabetical, but there are many more. If you want to add them in the graphical user interface, basically you want to activate plugins. So for instance, on the 18th of December, we're going to welcome Julien Tierney, who develops the topology toolkit, which is an extension for VTK that allows people to do topological data analysis. It's packaged as a Paraview plugin. But by default, the interface is already so crowded that not everything is there by default. But just to know that this is where most of it happens. Extractors never used it. Okay, tools. Okay, tools manage plugins. This is important. You want to go there and you want to load different things. So for instance, what Julien Tierney does is here. Okay, topology toolkit. I could auto-load it, reload, and then I would get the TTK, probably. What I always load is the analyze nifty reader writer, because I tend to work with 3D volumetric images. That's what I'm going to show you, which are encoded as .nii or .nii.gz. And by default, I don't know why Paraview doesn't want to open it. You need to just tick this mark, reload Paraview, and it works. Okay. So that's Paraview. Okay, I never use that either. So then you have those buttons. This is a bit useless. This is important if you want to do movies. Okay, the convention with Paraview is that if you feed it data, if you feed it files whose names end with a number, it's going to understand that you want to do a movie. So if you have step_1, step_2, step_3, and you drag and drop it, it's not going to open 3 files. It's going to open 1 file. And then if you play with those arrows, you're going to scroll through all your steps. Okay, so this is the way you do animation with Paraview. Okay. Then those are other things, but I'm going to show you. So let's load some example data, fully anonymized, an nii.gz file. By default, Paraview does not want to open compressed files, so I had to unzip it. So I go from 66 megabytes to 126 megabytes, but okay. But now I have something, an NII 3D image that I can drag and drop here. Okay, and now if I basically to see it, I click on apply, and now bam, I have my data. But by default, volumetric images are a bit heavy, so it just displays the outline. Okay, so just to be clear, what is important here, just on information, you see what your data is about. So it's a file, it's a big image, and you have some numbers that range from -20K to 31K. Okay. So representation outline. I want to do something more interesting. So I'm going to click on volume. Okay. And now volume, ta-da, I start to see something, okay? But by default, it doesn't look great. So I need to edit the color map, okay? So how to do that? Okay, you see the next menu is this. So I click here on, I could click here on edits, but that jumps here, okay? So with this, I'm going to edit the color map, but the first thing I need to do with CT scans is actually just to clip the values, because by default, you have values from minus 20K to 30K, but actually everything interesting happens between like 0 and 500. So this is what I'm going to do. Here, I'm going to rescale to a custom range, 0 to 500. I'm going to say OK, and then ta-dam, you see what is happening, right? So this is actually someone with a very nasty fracture. Okay. Now, what is happening here is that this is volumetric rendering. Values closer to 500 are colored in red. Values closer to 0 are colored in blue. And here you have a ramp, which is the opacity of my data. So by default here, red is opaque and blue is transparent. So if I want to highlight the bones, what I can do is I can edit my color map. That's why Paraview is really great, is that you can do all of that interactively and it works, okay? So that's a simple thing to do. And also here, I can edit the color map. If I want to change the ramp, I can. Or maybe you can say, oh, I'm going to change. So to reverse, I can click here, okay? To choose a different color map, I click here. So you have tons of small buttons. I'm highlighting the important ones. Maybe I like the bone one. Bone MATLAB, apply. Okay, and it looks okay. Let's say. So this is for volumetric rendering, and then okay, this is the intimidating stuff. So just to be clear, here I toggle the advanced properties with this button. Okay, here I have less options, but some of them I actually like them. So I always toggle the advanced properties. Okay, so then you have stuff here. For instance, map scalars, it's toggled by default, but if you untoggle it, it's going to try to interpret the values as RGB values. But here it's not going to work because you do not have 3 values per pixel. So you have tons of things. Maybe the important thing here, like the properties that are related to volume rendering, I can decide to shade things with ambient occlusion, and it's going to look like this, maybe a bit better. Okay, and then you have other things like, for instance, if I want to enable camera parallel projection, I can do that, and then it feels more isometric, and I prefer that. Okay, and then you could enable ray tracing also, but for volume, it's not very useful. So now the whole thing about Paraview is that all the functions, all the BTK functions are accessible as filters. So what if I want to extract the bones from this volume? I can just, for now, extract a level set. And the way to do that, actually, so here you have the buttons that specify the view. And here you have the buttons that specify the most commonly used filters. So for instance, if you want to apply a piecewise transformation, you click on calculator and you specify your formula and you edit your values. If you want to get an iso line or an iso surface, you click here for contour. It's also in the filter menu in alphabetical /contour. Okay, so that's what I do. Contour, and now in contour, you have to specify values. If you want to have several sheets, you can do that, but for today, I'm just going to extract the contour level set at 300. So I apply. Bam, I get this. So now it changed my color map, but actually here you see that both my volume and my contour are visible. But I'm not interested in my volume anymore. I'm just interested in my contour. I get it. So now I can zoom. By default, here it's represented as a surface. I could represent it as a point cloud, but it's very high resolution, so it's not very useful. I could represent it as a wireframe, you know, represent it as surface with edges, you know, why not? But okay, let's stick to surface. And then by default, it's colored using my color map, but you know, here I'm happier with a constant color. So I explicitly say, no, I want a solid color, and I'm going to pick something that looks a bit bony. Maybe something like that. Oh, it's not too great, but okay, let's go with that. It doesn't look, sorry, it really doesn't look like a bone. Okay. So now it's a mesh. So everything I showed you earlier can be applied. What? Yes. What?
I think he should.
Yes. Okay.
Because if we want to have questions.
Yeah. Okay.
And because there is a class.
Okay. So final 2 minutes. Yeah. Final 2 minutes. That everything I showed you with PBR, etc., it's there. It's in the lighting thing. So by default, it's Guru, but if you want to use PBR, you can. Okay. Then you set. Let's use a rough surface, etc. So by default, it's a bit dull. But basically, the idea is that if you scroll down, you have you can use tone mapping to increase the exposure. It looks like that. You can use ambient occlusion, you know, and it starts looking pretty good. And then, if you want to do the warp normal tricks, you have filters to do it. You know, so warp by vector. Let's go. Normals apply. So I get my second one. I color it black. I will cull the front face. Here, I'll show it. So that's how you get this kind of rendering in Paraview. And then you can also play around with ray tracing. So like here, I enable ray tracing. Raycaster is a bit bad. I prefer Path Tracer. So it's slower by default, it's noisy, but you can increase the number of samples of ray light that are simulated by pixel. You get this. Here it's a bit too overexposed, so I'm going to do that. No, okay. And so that's how with Paraview you get those kind of rendering. And then you can edit properties to change the background, etc., etc. And so, okay, I showed you everything I wanted to show today. I hope you're going to find the tutorial useful. And thank you for your attention. Okay, so if you have questions, or we can come back upstairs as you wish.
And maybe a small question that I had, playing around with volumes in BTK, but I suppose it's the same as by Vista.
Yeah.
Does it handle multiple volumes in the same scene? Or
not really. I've never
experienced the last volume you add is.
Yes.
There's not even.
Yes. No, I agree. Yeah. You'd have to fuse them using the algorithm you like, and then render a single volume at a time. Okay. Yeah, otherwise, it looks.
And when displaying a volume in a mesh, is the mesh correctly positioned within the volume? Or
if I remember correctly, it's not too great. Yeah. So typically, I use volumes, to play around to explore the data, and then for nice graphics, I always extract contours.
Yes, so I also have some things for 3D, but does it handle like image?
Yes.
Like 2D image.
Yes. So you could do everything in 2D. Actually, like here, for instance, there's a 2D mode. You change. Yeah. So you probably can, but to be honest, I think if you want to stick to 2D, you maybe have better libraries. I don't know.
I'm just specifically interested in the movie.
Because
it was really simple, and it's always hard. So I've been struggling and moving from one library to another, and constantly change.
Okay.
So yeah.
Yes. So basically, what you can do is simply you set your camera position to XY, parallel projection.
Yeah.
You do a 3D with 0 coordinate.
Okay.
And that's how I would do it.
Okay.
Joanne?
Yeah, I am. Yeah, so about PyVista also, is there a way to have, like everything you described, to have a GUI, like a window with, is it something that is possible with PyVista to render a window with options?
So it's very easy to do with Vido. You have tons of tutorials. I think you have some tutorials on how to do it with PyVista. But me, I've never used them, so
because I think it would be useful for some people to try. So you render a default view, and then you want to try many options by just clicking on, so you see directly how it works, and then maybe you can reproduce the code that leads to the same rendering.
Yes. So basically, that's how I use Paraview. I use Paraview to check what I want to do, and then I implement it in PyVista. But it's very likely that it's doable with, like if I type PyVista gallery, it's great. I have tons of examples. And I think some of them are with a graphical user interface. So it's a terrible Eduroam internet is striking. But okay, mesh creation, filtering, plotting, widgets. Okay, so you have some stuff here. Okay, but the most impressive ones are very clearly the Vido documentation. Like here you have, and basically the thing is that Vido and PyVista are just two thin wrappers on top of PyVTK, so it's very much interoperable. If you want to show off, it's a bit crazy.
Do we have simple ways to interact with the data? Just to, for instance, in the last example, we wanted to press thing.
Yes.
You see mouse, bones.
Yes. So I mean, it's really well done. So, but it's just that I never use that in my work. So
I think there is some way. Okay.
Yes.
No, don't do that because I think here you track things.
Yeah.
And for example, if you want to get some dish, because in fact it's not completely dish.
Yeah.
So if you want to get back to the
Yes.
And so you may want to clean things and interact with your clean things.
Yes. So WebVisual did some of that for scikit-learn, but I never actually did it myself. So not yet. Okay. Yeah, Joël.
Last question. Is it possible to add fog?
Fog?
Yeah.
Yes. So there is some blur, which is their depth of field. Depth. So this is very much supported, I think. If this is what you're thinking of, I never use that either. And real fog, I don't know.
No. Is it? I don't know. I cannot tell you.
Yes. No, sorry. But it's not PyVista, it's Eduroam.
No, because sometimes it's really. I know at least once I did a 3D figure and really with fog added.
Yes.
So you could see less well. I mean, the background was. I mean, the things that were behind were less visible.
Yeah.
Was really helpful for understanding the. 3D.
Yes. Oh, you're right. So maybe I don't know. I have to check.
Okay. This is more than.
Yeah.
It's not fog. It's like,
it's blur. It's like changing your lens or something. Yeah.
Okay.
Let's try PyVista fog. I have no idea.
Actually, I don't know if it.
No, frog. So probably no. I don't know.
En fait, ça dépend de la géométrie.
No, but
Actually, it was for, if you remember, Nicolas Chambre used to work with I mean, as a version, it was yeah, but they worked on surfaces. And that were pretty much like squares.
Yeah.
So if you use a shadow,
Yes, yes, yes.
well, sorry, because there was no shadow.
Yes, yes, yes.
It was not like complicated geometry like you are, but then to see what was behind our prompts, which was really helpful to add fog like.
Okay, now you're right. I know maybe there's a trick, like what I showed you with inflating. Because the basic way would be if you had access to the Z buffer, you could shade things like that. Okay, so I think we're good for today. Apologies for the delay, etc. I hope you enjoyed it.
So